Okay, we're beginning section 19.4, motion of a charged particle in the magnetic field. Um, and let's go to the next slide. Let's consider the case of a positively charged particle moving in a uniform magnetic field so that the direction of the particle's velocity is perpendicular to the field, as in the figure here. The label B in and the crosses tell us that B is directed into the page. So if you think of an arrow, on one side of the arrow you have the point, and on the opposite end of the arrow you have the fletching, the feathers that stabilize the arrow. So if you point it on end, you're looking at the fletching, you're looking at the little feathers. If you were seeing the point, then the magnetic field would be coming out of the page. Okay. Let's apply the right-hand rule to the particle at the bottom of the circle. The direction of the magnetic force there is upward. The force causes the particle to change its direction and to follow a curved path. So if we start at the bottom, the B field is this way, the velocity is this way, and so the force is upward. Okay. If you apply the right-hand rule to the particle at other points in the circle, you can see that the magnetic force is always directed toward the center of the circular path. So the magnetic force causes a centripetal acceleration which changes only the direction of V and not its magnitude. Because F produces the centripetal acceleration, we can equate its magnitude, QVB, in this case, to the mass of the particle multiplied by the centripetal acceleration V squared R. We can use Newton's second law to write the equation shown. Force equals QVB equals mv squared over R. Okay, let's solve for R. Hello. Let's solve for R. There you go. If we bring QVB, if we bring R to the left side of the equal sign and we take QVB to the denominator on the right-hand side, you'll see that the V cancels out with one of the V's and the V squared, and we're left with mv over QB. Okay, this equation says that the radius of the path is proportional to the momentum mv of the particle and is inversely proportional to the charge and the magnetic field. This equation is often called the cyclotron equation because it's used in the design of these instruments called cyclotrons, popularly known as atom smashers. Okay, if the initial direction of the velocity of the charged particle is not perpendicular to the magnetic field as shown in the picture here, the path followed by the particle is a spiral called a helix along the magnetic field lines. And a lot of the energetic particles that come from the sun that travel the magnetic fields that end up in the aurora borealis and the aurora australis do indeed follow a helical path. Okay, let's talk for a minute about notation. If B is directed into the page, as in the figure on the left, we use a series of green crosses representing the tails of arrows, or as I call it, the fletching. If B is directed out of the page, as in the figure on the right, we use a series of green dots representing the tips of arrows. If B lies in the plane of the page, we use a series of green field lines with arrowheads. This ends this section on motion of a charged particle in magnetic fields. The next section is section 19.5, magnetic force on a current carrying conductor.